Hello. In this video, I'm going to explain Vsepr theory. Vsepr stands for valence shell electron pair repulsion. So Vsepr is an acronym, V-S-E-P-R. And this is the theory that we use to come up with the shapes of molecules at a very, very small level. So the basic idea of this theory is that every bond or every pair of electrons will repel every other pair of electrons. This makes sense because they are similar in charge. They're negative. So because of this, they want to repel each other to the furthest possible extent. So they want to get as far away from each other as possible. And because this allows it then to get the lowest energy shape that it possibly can be. So if I start off with a very, very simple structure, and move this here. Let's start off with something like beryllium dichloride or beryllium chloride. So beryllium has two electrons, so it'll form two covalent bonds. And it can form in a bunch of different ways. It can be like this, or like up and down. But what happens is beryllium chloride wants to get these two bonds as far away from each other as possible. So they want to repel each other, push each other apart. So in reality, beryllium chloride actually has a structure like a line. It's called linear, like this. So this is linear. And we get a degree or an angle between them of 180 degrees. 180. Excuse my drawing. So these bonds want to repulse each other as far away as possible. So taking a look at another kind of example, let's take a look at aluminum, let's say tribromide. So aluminum tribromide, so aluminum has 3 electrons, 2, 3, forming bonds with its bromine. I'm just going to ignore the lone pairs on bromine for now. And these bonds want to push each other as far away from each other as they possibly can. So this is the repulsion part. It's electron pair, so electron pair in the bond repulsing each other. So this, I'm just going to move for a bit, this then becomes Al, and I get 3 bonds that are now 120 degrees from each other. So now these bonds are all equal, to all equal distance. It's now 120. So these bonds are now as maximum distance as they can be from each other. So if I got 3 bond pairs here, 3 bonds, they're all going to be 120 degrees from each other. And that's the maximum they can be. But as soon as I go to 4 bond pairs, so let's do CH4. So we normally draw this like this, kind of like northeast southwest, and this gives the impression that it should be 90 degrees. But in reality, when we take a look at now in 3 dimensions, it becomes slightly different. It becomes a tetrahedral. So we have one hydrogen here, another hydrogen going here, and now we draw a dashed line to indicate going behind my screen here. So this is actually going into or behind the screen. That's hydrogen, and we draw a solid kind of wedge here to indicate it's coming out of the screen. And so these guys between all of them are going to be 109.5 degrees. And so if we take a look at this as a tetrahedral shape, and a tetrahedral is it's like a triangle pyramid, like so. And with carbon at the center and hydrogens kind of here at the points. And so it forms kind of bonds to each one of them, like so. And so that's how we get this kind of 109.5, and it's just the angle between the two hydrogens and the carbon. So, and it gets bigger like that. If I take a look at now a 5 bonds, so I'll move this up, and some of the 5 bonds, actually the first thing really with 5 bonds is going to be phosphorus pentachloride, because phosphorus can exceed its octet. Well, now we're going to get a shape, not 5 flat around it. We're going to get the phosphorus, and then we're going to get one in the plane, another one above, another one below, and then we're going to get two others kind of coming in and out of the plane. Now this shape is the CCl, Cl, 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 Cl. So these guys actually form 2 different sets of bond angles. Between the ones in the plane, which is between here and here, and then here and here, and then here and here, they're all going to be 90 degrees. But between the 3 in the middle, they're all going to be 120. So it actually forms 2 different planes. So we get like a side plane and a vertical plane. So we get 2 sets. Now the last one we're going to show, and actually this is actually called a trigonal bipyramidal. And that's because we get 2 trigonal pyramids, so like from here to here to here, just like kind of our tetrahedral, 2 trigonal pyramids on top of each other. So that's one, and I'll draw the second one kind of here in red, like this. The last shape that I'll kind of show you is going to be the octahedral shape. And take a look at SF6. So it's another one that can exceed the octet. So sulfur will have one kind of bond pair above, one kind of bond pair below, and it's going to have 4 in this kind of XY plane, like this. So remember, the wedges come out of the plane and the dashed lines go into the plane, and we get our fluorines kind of around it, like so. And all of these guys, every single one, is going to be 90 degrees to each other. No matter which way you turn it, it's always going to be 90 degrees. And it's totally symmetrical. And this shape is called octahedral. Because if I connect everything, it's actually going to look like 2 square-based pyramids, like 2 Egyptian pyramids, but it will have like 8 equal sides, kind of like so. So it's going to be my octahedral shape. So we have now all the different shapes. So we have octahedral, and if I take a look at everything else, then here I have my tetrahedral shape for carbon. So this is tetrahedral. Then taking a look at my aluminum bromide, well, if it forms a shape like this, I can connect it together and actually just forms a triangle. But we have to be a little bit more specific, so we call it a trigonal planar shape because it's in a plane. Planar. So we got trigonal planar, and we got tetrahedral down here. Oops. And this one, really easy. It's just going to be linear. So I've broken down all the different angles. Now I'm going to take a look at, just for the last couple minutes here, I'm going to take a look at one more type of shape, and I'm going to expand on these kind of tetrahedral shapes. Well, if I have something like NH3, ammonia, a very common molecule, well, nitrogen here, it's got a lone pair. It's still going to conform to this tetrahedral shape because it still has four pairs of electrons. It's got the 3 bonded pairs here of hydrogen, and it's also got this kind of lone pair. And the lone pair still occupies space, so we still have to count it. So it kind of occupies this space above. And it still forms an overall tetrahedral. But because we don't really include the lone pair in its actual shape, it's only got this kind of pyramid here, like this. So unlike the trigonal planar one, this one's actually three-dimensional. So we call it trigonal pyramidal. So it's trigonal pyramidal. So it's got like a triangular base and it's like a pyramid, no matter which way we hold it. Now the thing about this one though is the lone pairs here, they actually exert more force on the bonded pair. So they actually push harder. So as a result, the angle between now the bonded pairs here, it shrinks a bit. And it shrinks by about 2.5 degrees. So for this one lone pair pushing on the bonded pairs, the angle between all the other bonded pairs is now 107 degrees. And that's because this one is not an equal pressure, it actually pushes more, and so it forces them further together. So they're now, instead of being 109.5, they're 107. And the last one I'm going to do, also the tetrahedral, is going to be our good friend water. Now H2O, we draw it out actually like this. It would be HO, 2 lone pairs here in the middle, and hydrogen here. Now I said before, we draw it as kind of this bend structure because, well, the lone pairs actually occupy space. And that's because these lone pairs are occupying like the other 2 posts of the tetrahedral. So I draw the tetrahedral like this, and I got my oxygen in the middle, and hydrogen here. Well, these other 2 points, well, they're taken by the lone pairs, like this. So we get kind of like this bent structure, and these are kind of lone pairs, and they're orbitals. And so that's why it's kind of like this, like bent structure, and actually it is called bent or angular. And because it has 2 lone pairs instead of 1, these lone pairs actually push it even closer together. So this angle in between here is now 104.5 degrees. It gets even 2.5 degrees closer, so it's about 2.5 per lone pair of electrons, and they get closer. And this is pretty much the Vsepr shape. So now we're taking like the idea of our Lewis diagrams and we're applying a very simple theory in order to get like their more complex 3-dimensional shapes. and we'll practice some of these with the next class.